Today we are starting chapter 9, and we're doing a combination of the content that the learning goals for 9.1.2 and 9.1.4 because they're very related. And we'll be learning about transformations of functions, two special functions in particular, one the quadratic function and the other is the absolute value function. So the learning goal for today is to learn how to use transformations to graph quadratic functions and absolute value functions in an efficient, quick way by just looking at the equation, identifying some key features, and then just being able to put the graph on there and move on. So the idea is it would take you only a minute or two to graph a parabola with a relatively complicated looking equation once you know what all these numbers actually represent. And then the absolute value function actually makes these V-shaped graphs. So we're looking at parabola, U-like graphs, these curves, and these V-shaped graphs, and they have a lot in common the way that their equations will be structured today. So we're going to use a similar method for graphing each of these types of functions. Okay. So our essential question, how do you graph quadratic functions in vertex form? And how do you use transformations to graph absolute value functions? So to start, we're going to go over the different forms of quadratic functions that we will work with in this class. And the first two we've spent quite a bit of time on already in previous sections. So our first format of the quadratic function is the standard form. We use this a lot to get set up before we factor it or do other kinds of manipulations to the equation. We get it into standard form where ax squared plus bx plus c. And the standard form is it's kind of like the most complicated format if we're trying to graph, because what it means is we have to build a table. We need lots of different points on the table, and then we can plot those points. But it takes a lot of sort of algebraic calculations to do that. One thing we can identify really clearly from the standard form, though, is where the y-intercept is on the graph. So if you plug a 0 for x, you get a coordinate 0, comma, whatever the y is. And in this case, the c is what would be left. So that's what gives you your y-intercept, 0, comma, c. Then we've also spent some time working with factored form, which is also called intercept form. And factored form is basically when you take the standard form and factor it, and then the two factors help us to identify the x-intercepts or the zeros of the graph. And we've done a lot of solving quadratics where we plug in a 0 for y and solve for x. They also help us identify those x-intercepts on the graph itself. So P and Q would represent the x-intercepts. And then to graph using factored form, we'd want to then find the halfway point between the two x-intercepts to get the x-coordinate of the vertex, plug it back into the equation to get the y-coordinate of the vertex. And that's a whole process in and of itself as well. The third format for a quadratic function that we use quite a bit in you'll see it again in your math career is called vertex form. And sometimes it's referred to as the graphing form as well. And the reason why is because this is probably the most straightforward of the three formats in order to graph quickly, to graph a quadratic equation quickly. So what's special about the vertex form is that it's formatted differently than factored form. It has a perfect square in there. This is actually related to perfect square form of a quadratic, which we've spent some time solving in the past. And this x minus h quantity squared and then plus k, the h and the k actually give us the vertex of the parabola itself. Like right away, you could identify the vertex. And once you know the vertex, the thing that's left to do is to make sure that the shape of your parabola is correct for your equation. And that brings us to this one other element that happens to be in all three of these formats, which is the value of A. So this leading coefficient A is the same in each of these three formats. And A tells us about how the parabola is shaped. Like, is it very, very steep, or is it more wide and like slow growing, or is it flipped upside down and reflecting opening downward? So the A value has a lot to do with the shape and size of the curve once you've located that key point, the vertex for each of these. And we're going to spend all our energy on vertex form today. All right, so to start, remember the learning goal today was all about how we use transformations to graph a quadratic function or an absolute value function. And a transformation is a translation, like a slide, left, right, up or down, a rotation, a turn, or a reflection. We're not going to use rotations at all today. We're just going to be looking at translations mostly, and reflections. Once in a while, we'll reflect. So what we're going to do is we're going to identify what we call a parent function. And every single family of functions has a parent function. The quadratic parent function is y equals x squared. It is basically the function that we start with always, and then we perform transformations on it by manipulating the equation and by moving it around on the graph. So we start with y equals x squared, and then we might do a horizontal shift to the right or to the left, or a vertical shift and move it up or down, or maybe reflect it and it turns downward and opens downward. But we always start with this parent function, also known as the mother function. So that's just funny, so I have to throw that in there. All right, so we're going to graph the parent function for all parabolas, and then we're going to use that parent function as sort of a starting point with every single graph we do going forward of a parabola. So in order to fill in the table, we won't fill in the table much today, but we will for the parent function. So remember, when you're filling in a table, you're plugging in these x values that are given to us in this x column, and we'll find the y's that are the outputs. So when we input a -2 squared is +4. So our output is 4. Input a -1 squared is +1. Oops. Okay. Input is 0 squared is 0. 1 squared is 1, and 2 squared is 4. And we could continue this. The next one would be 3. Input 3, output 9. 3 squared is 9. Input 4, output 16. Like, you could continue on, but this is enough for what we need. And now I'm going to go ahead and graph these points. So we have a point at 0, 0. That's going to be our sort of pivot, our vertex point. And then to the right, we have at 1, 1. And symmetrically on the left, we have -1, 1. And then we have over 2 up 4 to 2, 4, and over 2 up 4. And then the other direction, -2, 4. And our parabola looks something like this. And I want to make sure that you remember that the parabola's shape, the quadratic function shape, is a parabola. It's a curve. It looks more like a U than a V. So please, please, please don't graph a pointed V shape right now. If you graph a V, what you're doing is you're actually graphing an absolute value function, and that we will learn about at the end of this lesson. So it's a different family of functions altogether. The quadratic function is the quadratic family of functions, and they will always be parabolic. They will always have this kind of shape. All right, so this is our parent function, our mother function. This is y equals x squared, and it has a vertex at 0, 0. You can see how the vertex is in the middle here of the table. And you can see how we have symmetry on either side of the vertex in our outputs. So you see how we have like, here's a 1 and a 1, and then a 4 and a 4. We have this like symmetrical outputs in our table. And this is an important detail for parabolas that helps us to make sure that we have our symmetry on our graph. Okay. So I'm going to go ahead and clear here and move forward. So now we're going to look at the vertex form of a quadratic function and think about how we're sort of adjusting the y equals x squared parent function in different ways with a, h, and k. So remember the parent function that we just graphed on the previous slide is y equals x squared. This is the parent function. So I'm just making a note of it over here so we can refer to it. So this parent function y equals x squared technically is in vertex form. It's just the simplest vertex form you can have. Our leading coefficient a for our, that's my cat, our parent function, a, when you don't see a number here, there's a 1. So the parent function has an a that's 1. Then there's this h value here. We don't have an h showing up in our parent function, so it's a 0. And the k value here. And again, we don't have one of those, so it's a 0. But as we adjust these to be other numbers besides 1, 0, and 0, we start seeing like this behavior come out, this transformation behavior, and we're moving our graph around and changing its like how steep it is or which direction it opens. So A, that leading coefficient, determines the direction of the opening and the shape of the parabola. And we will get into this in more detail in some examples later on. H, the value inside the parentheses with x, see how we have x minus h? H represents a horizontal translation, so a shift to the right or to the left. K, adding a constant at the end of the equation here, outside of the parentheses, is a vertical translation. So the K represents how we move up and down. Just take that whole parent function and move it up or down. And then the H and the K combined together actually give us the vertex of the function. And this is really like the big takeaway here. The vertex of a quadratic function in vertex form, this is why we call it vertex form, should be obvious, like you should be able to see it directly in the equation itself. So when you look at an equation and there's numbers in there, you can identify by sight where the vertex is, and that's why we call it vertex form. So what we're going to do now is we're going to look at each of these different changes like one at a time. So we're going to start by looking at what happens when all we do is manipulate h. That means make a horizontal translation of our parent function. Then what happens when we just, adjust by a value of k, so like a vertical translation. And then what happens if we change a, change the size and the shape of the thing. And then what happens in situations where we have all three of those numbers are something different than what the parent function has, and look at the combination. All right. Okay, so let's start with h, the horizontal shift. So h moves our graph to the right or to the left. So you can see how we have some details here that we can look at here. So we have this general, given the function y equals x minus h squared. So notice how a is not sort of included in there, k is not really included in there. So we're just focusing in on messing with the h value. And there's some notes here for you. So if h is greater than 0, then the graph will move to the right h units. When h is less than 0, then the graph will move to the left h units. Now this is where it gets a little bit weird. Notice how the equation has a minus sign here. That affects the way that we read the numbers in our equation. So in this problem, in part A, we're going to describe how the numbers change the graph of the parent function y equals x squared, and then we're going to graph it. This x minus 4 actually tells us that our h value is positive 4. This is the weirdest one of all, so we're starting with it. But so what this means is, think about it. If you had h was 4 and you plugged a 4 in for h right here, it would look like x minus 4 because the equation itself has a minus. So when you see a minus inside the parentheses, the h value is the opposite. So if it looks like minus inside, it will be a positive h value. It's the opposite. And what this tells us then, since h is 4, is that we're going to translate to the right 4 units. We're going to translate our graph of our parent function to the right 4 units because our h is positive. It looks negative, but it's positive. So our graph now will do this. Okay, we're going to start, the parent function's graphed for us. So it's going to be a translation of that graph that's already on there to the right 4 units. So I started 0, 0, the original vertex, and I moved to the right 4 units, and that's my new vertex. And now what's left to do is to figure out the steepness of the graph. And because my leading coefficient in front of the parentheses is not showing up, it's a 1 just like it is in the parent function. So that means it's the same size and shape as the parent function, the purple one, the violet one on the graph. So here's how I identify the shape of this thing. The original function, if I start at 0, 0, to get to the next point, I went over 1, up 1. That took me to the second point that I knew from my graph. So on my new graph, I'm going to go from my new vertex over 1, up 1, and that's going to get me a new point. And there's symmetry in these, so I'll also go to the left 1 and up 1. And then I need another point. So the second point I had on the original parabola was when I went over 2, up 4. Because 2 squared is 4. So I'm going to do that for the new one as well, over 2, up 4, and that will get me, and then I need a mirror image of that on the left 2, up 4, and that will get me the points to make an accurate parabola. So here we go. Oops. Okay, good enough-ish. All right, so I want to keep the size and shape the same, so this is how I do it. So again, just to go back over that, the way that the original parabola, the y equals x squared parabola, was formatted was I had a 0, 0 vertex, and I went to the right 1 and up 1 to get a second point, and to the left 1 and up 1 to get a second point. And then to get another point, I would go over 2, up 4. So then over 2, up 4 to get this one. So I'm doing the same moves here, over 1, up 1, over 2, up 4. And then having symmetry. And I'll keep on talking about this over 1, up 1, over 2, up 4 thing for each of the graphs that we do going forward. All right, so now we're going to do part B. So first things first, let's identify our H. So we have a +2 here, which means our H is the opposite of that, which is -2. Because if we substitute a -2 into the original function at the top in the blue box, x minus a -2 would look like x plus 2. So the sign gets changed. So we have a -2h, which tells us to translate left 2 units. So just to recap, if you see a minus in there, you move right. If you see a plus in there, you move left. It's like the opposite of what you think. And now we're going to graph the curve. So I'm going to remember it's always a translation of the original parent function. So I'm going to move from 0, 0, left 2 units. And then I need to count out the size of my parabola. So from that point, right 1, up 1, left 1, up 1. right 2, up 4, left 2, up 4, and connect the dots. Okay. Okay, so now we're going to look at K. What happens when we adjust our K value in our vertex form? This is a vertical shift. So what's now happening is y equals x squared plus K. The K is an adjustment outside of the squared term rather than inside like the H. So with K, it's actually more straightforward. If K is greater than 0, so if K is greater than 0, a positive number, then we move the parent function up. And if K is negative, less than 0, you move it down. So this one's actually more intuitive. It's like if you see a +3, like in part A, you're going to move the whole graph just up 3 units. Easy peasy. All right, so let's do it. So we've got to identify our K. So here, this 3 is telling us that we have a K value of 3. We don't change the sign for K, only H. The H is the weird one. And this K equal to 3 tells us a translate up 3 units. So, and then graphing is essentially the same. So what we do is we go to our graph, we go from 0, 0. We always start where the parent function has a vertex at 0, 0, and we go up 3 units. There's our new key point. And then we count out the size of our parabola. So remember, from that point, we go right 1, up 1, left 1, up 1, right 2, up 4, left 2, up 4, and connect the dots with a nice curve. All right. For part B, it's the same idea, but this time we're going to go downward. So I'm going to change my color, and this -1 right here tells me that my K value now is -1. And that means that we are going to translate down 1 unit. But the graphing process is the same once we do that shift. So go from 0, 0, move down 1 unit, and then count out my graph the same way as we keep on doing it over and over again. So from that new point, right 1, up 1, left 1, up 1, right 2, up 4, left 2, up 4, and there we go. Kind of squishy because it's only a 1 unit lower, but hopefully you get the idea. All right, so now what we're going to do is put those two things together, the H, the horizontal shift, the K, the vertical shift, and look at how HK represents the vertex in combination. So we're going to have both a horizontal and a vertical shift in this problem. So you can see how we have an H value, right? We've got something inside the parentheses with the X, and we also have a K value, a number added or subtracted at the end here. So let's identify those numbers. So we have, remember, it's always opposite of what we see for H. So H is equal to -3. And if we thought about this in terms of a shift, this would be a left, right? We would move left 3 units. Like if we were thinking about this in terms of a transformation. And then the -2 out here is our K value. So K is equal to -2. And this would represent a downshift of 2 units. So we can still think about it in terms of translations, but we also, from this information, have found the vertex. So what we know from this is the vertex is HK. So see at the top, the title is H comma K, the vertex. So the vertex is HK, which means it is at -3, -2 for this problem. So we're going to use that vertex to help us regraph, the translated parabola. All right, so -3, -2. If I go from 0, 0, that is a shift left 3 and down 2. Left 3, down 2 takes us to -3, -2. So that makes sense with our vertex. There's our new vertex at -3, -2. And then the size and shape of this graph has not been affected. Do you see how in front of the parentheses, there's no new a value? So we haven't had to deal with this yet. So our size and our shape is the same as the parent function. So from that new vertex point at -3, -2, I'm going to go right 1, up 1, left 1, up 1, right 2, up 4, left 2, up 4. My dots are really not dot-like, sorry about that. But there is our translated parabola. And it also wants us to find the axis of symmetry. So we got the vertex, there's that. Now we're going to get the axis of symmetry. So the axis of symmetry is always a vertical line right through the center of your parabola. So it's going to be here. Oh my goodness, I draw a line. There it is. That is your axis of symmetry. Remember, the axis of symmetry always has an equation that's related to the x-coordinate of the vertex. So it's x equals -3. It's the x-coordinate of the vertex. All right, so this is everything we needed for this particular one. And you can see in this diagram on the right here how HK represents your vertex, how x equals h is your axis of symmetry. It's the x-coordinate of your vertex, so it's the h value in the vertex form of the equation. It's all connected. Okay, so here we have A, the direction of opening and shape of a parabola. So in the previous problems, our A has been 1, because when you don't see a number in front of a variable, there is a hidden 1. When A equals 1, the shape and direction of the parabola are exactly the same as the parent function. But what happens when A is not 1? So a couple of things I want to point out in these diagrams here. So in this first diagram right here, what we have is the scenario when A is negative. So do you see how the graph on the top in blue, A is greater than 0? That's when A is positive. It's upward. But when A is negative, it reflects downward. Another thing that happens is when we change A from being a 1 to being something else. So if the absolute value of A, so we don't worry about positive or negative, the negative would just flip it upside down. But our value of A, if A is greater than 1, like A is 2 or 3 or 4, it actually makes our graph steeper. It will make it grow faster. So it will, instead of just, like the parabola, the parent function has a certain size, it will make it grow faster than that. So it'll be a much narrower looking, like taller sort of parabola. If A is a number lower than 1, like 1/2, it will make the graph wider and slower growing, because it will like slow down its steepness. So in this example now, it says complete the table for the equation, graph the function, and describe how the numbers change the graph of y equals x squared, our parent function. So take a look. What we have here is an a value of 2. And based on what I just explained, an a value of 2 would make this graph steeper. So what we're going to do is look at how the numbers come out and how much steeper it will be. So let's substitute in our x values and get our y's that go with it. So when we substitute a -2 for x, we get y equals, so basically I'm just plugging into this equation here, y equals 2 times our x squared, right? And I'm just substituting in each of these x values on the table. So if we put a -2 in, what we get is -2 squared is 4, but then times by 2 would be 8. We plug in a -1. -1 squared is 1 times 2 is 2. 0 in will give us a 0 out. And then we'll have symmetry. Input a 1, we get out a 2. Input a 2, we get out another 8. So when we graph this, we still have 0, 0 as our vertex in the middle. You can see that right here, right? We have a 0, 0 point. But now we have -1, 2, +1, 2, -2, 8, +2, 8. And you can see how the parabola has become quite a bit steeper. All right, so now I'm going to point out something important to see. You know how the original function, we would get our points by going over 1, up 1, over 2, up 4. Well, now we're going over 1, up 2, over 2, up 8. The height of these steps is taller by double. These outputs are twice as big as the outputs from the parent function. I don't know if you remember those offhand, but the parent function had this kind of table. This is what the parent function's table looked like. Do you see how these numbers in the 2x squared table are twice as big as these numbers in the 1x squared table? So our outputs are doubled, which means each new point is twice as tall. So if we had a 3 in front for A, we would have a triple steep graph. If we had a 4 in front, it would be 4 times as steep. So this helps us to sort of describe what's happening here, that our graph is, the outputs are doubled. The outputs are doubled. So the graph is, oops, can spell. So the graph is twice as steep. The outputs are doubled, so the graph is twice as steep. Okay, so now what we're going to do is look at what happens if instead of A being a bigger number, what happens if A is a smaller number, like 1/2? So you can see here, our A is 1/2. All right, so when we start filling in the table, we plug in a -2 for x. -2 squared is +4, but then we take half of that. So it's 2. We plug in a -1. -1 squared is +1, but we times by 1/2, which means we output 1/2. 0 will still output a 0. And then we have our symmetry. So there's another 1/2 and another 2. So now when we go to graph these points, you can see 0, 0, 1, 1/2. Instead of over 1, up 1, it's over 1, up 1/2. It's half as steep. Oh my gosh, I can't even draw a point. This is so frustrating. Okay, here we go. Half, and then over 2, up 2, instead of up 4. 1/2, 2. So you can see how now our parabola has widened. It's half as tall from point to point. So what we have now is a parabola that's half as steep. And if you think about the outputs in the table, these numbers are half of the numbers from the parent function's outputs. So instead of 4, 2, or 4, 1, 0, 1, 4, it's 2, 1/2, 0, 1/2, 2. They're halved. All right, and then one last A value to address here, and that would be if our A is negative, what happens? So we want to get a good visual of that. So you can see how here we have a negative. That negative x squared just means that our A is -1. All right, and if A is -1, our inputs, when we get our outputs, all of our outputs will look just like the parent function, except for they will become negative. It will just make each output a negative rather than a positive. So that means we would output here a -4, -1, 0, 1, -1, excuse me, and -4. So this is the same exact size and shape as the parent function. It's just upside down. Look, -2, -4, -1, -1, 0, 0, 1, -1, and 2, -4. This is just an opening downward, perfect reflection of our parent function. These are arrows, by the way. So then we want to just describe this. This is reflection of the parent function. So it opens downwards. All right, so here in example 5, what we're looking at now is, what we're looking at now is equations where we have an A value other than 1, and we have an H value and a K value other than 0. So we've got a new vertex, so we have translations happening, and we have a change in the shape or direction opening of the parabola. So in part A, you can see we have A is negative, so I have a -1. We have a K, or an H, excuse me, in here, X -1 tells me H is 1, and then we have +4, which tells me K is 4. So just to remind you of each of these things, remember this tells us the A, this tells us the H, and this tells us the K. And I'm going to list them over on the side. So what we have here is we have an A of -1. And that's going to tell us to make our graph open downward. Okay, or reflect, right? And then we have an H. Remember, it's always the opposite of what you see. So we see -1 inside, so we're going to have an H of +1. We have a K of +4. And those two things together tell us that our vertex is at 1, 4, HK. And this is everything we need to have an accurate graph for this particular one. So again, we open down, but we don't change the size of the parabola, and we have a vertex at 1, 4. And these are the things that we need to have an accurate graph. So I'm going to go to 1, 4 and get my new vertex. It's right here. And then I'm going to make a downward opening parabola the same size and shape as the original parabola. So remember, the original parabola goes over 1, up 1. So for this new one, we're going to go over 1, down 1. and to the left, down 1, over 1, down 1 to the left. And then from the vertex over 2, down 4. And also in the other direction. And there we have it. All right, so now let's look at part B. So we have different numbers here. We have our A is 3, our H is going to be -4, and our K is -5. So let's list those. So we have A equals 3, and that tells us that we'll have 3 times as steep. So super steep by a factor of 3. All right, 3 times steeper. 3 times steeper than the parent function. Okay. And then we have our H and our K. So our H, remember H is always the opposite of what you see, so it's a -4. Our K is exactly what you see, so it's a -5. So this gives us our vertex at -4, -5. And that's all we need for an accurate graph. So we've got our 3 times steeper, and we've got our vertex at -4, -5. Okay, so now it's time to graph. So we're going to go to -4, -5, and get our new vertex. And then we need a 3 times steeper than our original graph. So see, the parent function is over 1, up 1, over 2, up 4. I need 3 times as tall. So for this one, from our new vertex, I'm going to go over 1, up 3, over 2, up 4 times 3, which is 3, 6, 9, 12. 3, 6, 9, 12. And then I need a matching couple of points on the other side. 12. There we go. And so our new parabola, oops, I missed it. Our new parabola is this steep looking thing, 3 times as steep as the parent function. 3 times as steep. And just to like reiterate that piece of this, do you see in the original how it's over 1, up 1 right here? So I'm just highlighting that little hop in green. And here it's over 1, up 3. That's a height of 3 for every 1 here. So that little like leap becomes steeper by whatever factor your A is. Okay, so now we're going to look at how absolute value functions behave very similarly to quadratic functions, in that we will have a parent function. We'll have a general equation with A, H, and K, and how we sort of approach each graph will even be the same. Just the shape of the graph won't be a parabola. So it won't be a U, it will look like a V. So let's go ahead and see what this absolute value V looks like by starting with the parent function and graphing it from a table. So the absolute value always is the distance from a number to 0. So if we find the distance of -2 to 0, that's 2 units. -1 to 0 is 1 unit. Absolute value of -1 is 1. Absolute value of 0 is 0. Absolute value of 1 is 1. And absolute value of 2 is 2. So notice how our outputs are not 4, 1, 0, 1, 4, like a parabola. They're 2, 1, 0, 1, 2. It's different. So now we graph them. And we still have this 0, 0 in the middle. And then we have 1, 1, 2, 2, and if we continued, we go to 3, 3, 4, 4, 5, 5, and we have -1, 1, -2, 2, -3, 3, -4, 4 in the other direction. So when we put in our curve, it's actually lines. So this makes it easy. You can use your line tool. Oops. And these are straight lines in each direction. And the parent function is special in that the lines, one, they mirror each other. So there's always symmetry. And the line on the right-hand side is going to always have like a slope that we care about. So the line on this has a slope of 1/1, the line on the right. And the slope on the left would be -1/1. But I just want to make note of the slope on the right because that is going to directly correlate with what our A value is. Our leading coefficient will tell us the slope of the right-hand side. All right, so there's our parent function. So all absolute value functions look like a V, every single one. Sometimes there will be a very tall, narrow V. Sometimes there'll be like a very wide open V. Sometimes they'll be upside down, but V's nonetheless. Okay, so now check this out. The general form of the absolute value function. It looks almost identical to the quadratic equation in vertex form. It has an A, it has an H, and it has a K. The difference is that it has absolute value lines instead of parentheses squared. But the things that, like the way that A, H, and K affect the graph is the same. So A will determine the direction of opening and steepness of the absolute value function. So if A is negative, the thing's reflected down. If A is a large number, it will get steeper, the slope will be bigger. If A is a number between 0 and 1, like 1/2, it will get wider and flatter, like it will grow slowly. H represents a horizontal translation, right and left. K is a vertical translation, up or down. And H and K together combine to make that vertex the point of the absolute value function. All right, so here we go. You can see how we have the parent function now graphed on both of these, and we're going to do some transforming of each of these graphs. So you can see how in part A, we have an H value adjusted. So remember, it's the opposite of what you see. So we have an H equals 3 here, +3, which means that it's a horizontal shift, a translate right 3 units. So now we go to graph, and I'm just going to go over 3 units. And then this is actually easier than the parabola because I didn't change the slope of the thing. It's the same shape as the parent function. So it's going to have a slope of 1 to the right, up 1/1, up 1/1, up 1/1, up 1/1 forever. And then a matching line on the left. So I can use my line tool to make a perfect straight line. And these lines will actually be parallel to the ones on the original parent function because they have the same slopes. So it'll all be parallel, which is nice. All right. This second problem, this is our K value, and that means that K equals 4, which tells us we have a vertical shift or a translation up 4 units. So I just do the same exact thing, except now we move up 4. And again, my slope to the right is 1. So it's up 1/1, up 1/1, up 1/1, and I mirror it on the left, and then draw in my lines. So the structure of the equation is so much like the parabola that we really do the same. We approach the problem the same way. We just make sure that our shape of our graph is in the right family of functions. Absolute value looks like a V. Quadratic looks like a parabola. All right, so now in example part C, you can see how here we have an A value that's changed and no H's and K's. So this means since A is equal to 2, this means that our graph will be twice as steep. Okay, so essentially that means the slope on the right-hand side will be 2 or 2 over 1. So I go ahead and I don't move my vertex because there's no HK translations. I just started 0, 0. And then instead of up 1 over 1, I'm going to go up 2 over 1, up 2 over 1, up 2 over 1, up 2 over 1, and mirror it on the left-hand side. And you can see now how we still have a V, but this time it's twice as steep. The slope on the right-hand side is 2 over 1 versus the parent function, which had a slope of 1 over 1, because that leading coefficient is 2. And then finally, our last example kind of puts all those things together. So we're going to be looking at all 3 parts of the equation adjusted. So what we have is an A value of 1/2. We have an H value of -2. We have a K value of -3. So we identify our new vertex and change our slope. And the slope on the right-hand side will be 1/2. So here we go. So A is equal to 1/2. That tells us our slope. Half is steep. Okay. And then we have here H is -2. Remember, it's always the opposite of what you see. And K is -3. And so together, those two things give us our vertex, which is at -2, -3. And now we graph. So -2, -3. So we locate our vertex down here at -2, -3. And then we count out our slope of 1/2 to the right. So we go rise 1, run 2, rise 1, run 2, rise 1, run 2. Slope is 1/2 and mirror it on the left-hand side. So rise 1, left 2, rise 1, left 2, like that. And you can see how we have now a wider, slower growing absolute value